I think
okay.
Requested. So many understood as required, which is I'm very happy about that. Requested is like kindly requested, but I'm very, very happy you're here because this is really we're fortunate to have this presentation today by Dr. Alissar Yehya. And I'll just say a few words and Dr. Alissar will take the floor. Dr. Alissar Yehya is a postdoctoral fellow at Harvard University at the John Paulson School of Engineering and Applied Sciences. She received her PhD from the University of Lille, North France in 2015, good distinction. Her thesis was on phase change materials for enhancing thermal performance in buildings, which will be the core of the presentation for today. And she also served as an assistant professor at the University of Artois after graduation in France before joining Harvard in 2016 with the Professor James Rice Geophysics Group. Her current research interests focus, aside on this, on thermo-hydromechanical problems with application on induced seismicity and glacier dynamics. Before her PhD, she graduated from the Lebanese University with a diploma in civil engineering. She got her master's at the University of Lille also with the Lebanese University in 2012. During her undergraduate work and after, she worked also as a practical engineer, structural and geotechnical engineer at Patek, Corey and Partners. And she has been a visiting researcher at several institutions, including once in the summer at AUB and at Florida Institute of Technology. She has a few journal publications and conferences, a conference paper on her record, several scholarships and grants, an outstanding award for best paper at the conference in Orlando, and finally, she also, just to let you know that Dr. Alissar is an applicant to a position in civil engineering at the department, and this lecture is part of her presentations for assessment and evaluation. And she'll be presenting, therefore, this core presentation on her research, but also some short background on her experiences in teaching and others, and also on other research which are also of interest to us. So please welcome Dr. Alissar, and you have the floor.
Thank you. Thank you. First, I would like to thank the faculty members for inviting me here and for giving me this opportunity to present my work and give you a little bit about my past experience from the Lebanese University to going to and working at Harvard. So the main presentation, or the main core of the presentation, would be on the numerical and experimental characterization of n-Octadecane, which is a promising phase change material. So we'll talk a little bit more about it in the research part. So here's a small outline for this presentation. I think I'm sorry. Okay, thank you. So the outline, I will start by introducing myself, a little introduction about my academic background and my experience both in research, teaching, and work. A little bit about my view or vision on teaching and my philosophy of teaching. I will highlight on the research projects, the main research project that I've worked on, mainly my part of my research project during my PhD on phase change materials, and also my experience at Harvard working on two projects, mainly glacier dynamics and induced seismicity. So I will also present some perspectives of how I see research in Lebanon, or what I'm looking forward to, especially with respect to the challenges that we will be facing with respect to the new era of energy production in Lebanon and also energy saving. So this was the hardest part, actually, of the presentation about introducing myself. I usually introduce myself as a researcher, teacher, and engineer. But also, if I want, as a researcher, I describe myself as a person that has a lot of ideas, and as a teacher, a passionate teacher, and an engineer that has enough tools to do his projects. But what I think fits me well is that I'm a dreamer that never gives up. I always envision a goal, envision something, put a plan, and try whatever ways to go and reach this plan. And one of the things that I've had in mind is going to Harvard, and I think I planned it well, and I ended up at Harvard. So currently I'm a postdoctoral fellow at Harvard School of Engineering and Applied Sciences, working with well-known Professor James Rice, principally in the project that I've already said, two main projects. I also had the opportunity to be a lecturer and a teaching assistant in his courses, mainly in the hydrology and environmental geomechanics courses and the mechanics in earth and environmental studies, where I fully prepared lectures and presented them for graduate level. I've also had the chance to advise different students in France and also at Harvard, and mainly I'm responsible formally on advising one student, which is Joe Young, a first-year graduate student. So my educational background, as Professor Mabsout said, I've done my PhD in civil engineering from University of Laboratory of University of Artois at the University of Lille, North France. I took my PhD with distinction. My master's degree was in co-tutel between the Lebanese University and the University of Lille 1. My diploma of engineering was in the Lebanese University in 2009, and between these two I had a work experience for about 3 years in Rafiq al-Khouri and Partners. So here's the previous experience. I will not focus a lot on that due to the lack of time. So it's mainly I was a teaching assistant in University of Artois between 2014 and 2016 during my PhD, and after that I was a researcher, visiting researcher in the summer of 2014 in Florida International University, working with Professor Michael Sikub. And in 2015, I was a visiting researcher in the American University of Beirut, where I proposed and did like a series of seminars and lectures with Professor Marwan Darwish in the CFD lab. In the engineering part, I've worked like as a civil engineer, structural and geotechnical engineer in Rafiq al-Khouri and Partners for about 3 years for development projects in Beirut, Abu Dhabi, Dubai, and Saudi Arabia. So my vision for teaching, I see, like, I will not go through details in this because I think we will meet after the presentation. So I see learning as a social and not a solitary activity. It's a take and give and interactive process between the teachers and the students. So in my teaching style, I adopt theory, practice, and interaction. So theory, I try to manage and to have like the best references, the best theoretical background, and the best preparation for the students, and encourage students to ask as much as to answer their questions. So when we promote asking strategy in the students, we develop their creativity more, and also I encourage analytical thinking besides the practical implementation. So the other thing that I focus on is the practice. As a civil engineer, because I do have this experience as a civil engineer, I've encountered a lot of students that have trouble in connecting theory to practice. And it's very important to know how to prone the students for real projects and how can they adapt these theories to real and practical projects. So this would be through proning them to real projects, through demonstrations, numerical and experimental both, and also through tasks and assignments to students. The other thing that's very important is the interaction among the students and between the teacher and the student by promoting for group work, give and take process, and also the design thinking. One of the things that I've learned at Harvard is that the importance of employing a design thinking strategy for groups. Like they think divergent thinking at first, where they think outside the box, and they start converging their ideas into a real or community engagement projects or other practical projects. So design thinking for me is very important as a new interactive teaching tool. And of course, through presentations and workshops that the students will be prone to or will be adapted to. So the teaching experience I had besides the courses at Harvard, were mainly in France and for courses in fluid networks, fluid dynamics, energy performance of buildings, thermal performance of buildings, and geotechnical engineering and foundation design. I also had the chance to follow up with students in the undergraduate and the graduate levels. So now we go to the main part, my PhD research. Actually, my PhD research was not limited to the phase change materials. The major part was for the numerical method itself and implementing it for other applications. But one of the main applications that had been for my thesis is the phase change materials. And I will present today the numerical and experimental characterization of a very promising phase change material, which is n-Octadecane. And I will talk a little bit about that and the applications of this particular material in buildings as a material building. So this was done by, my thesis director was Professor Hassan Naji, and my co-director was Professor Laurent Zalewski. So what is a phase change material? A phase change material is a material of high latent heat of fusion and is capable by, when solidifying and melting, to store and release energy. So for example, when the material is at solid state, one particular thing about phase change materials is they are selected with melting points that lie within the human comfort range of human beings according to the temperature. So when, for example, this is a solid material, phase change material, when the temperature rises and rises till the melting temperature of the phase change material, which is the thermal comfort temperature of human beings, the material melts, and the excess of heat is used to as latent heat or to change the material from solid to liquid, and so the material remains constant. So it's in a way to regulate the ambient temperature and avoid some fluctuations in the ambient temperatures and improve the human thermal comfort. So one of the ideas is that it increases the thermal capacity. For example, if we look at all traditional houses, we see that these houses that have thick walls, they are cooler in the summer and warmer in the winter because of their high thermal capacity. But now, the modern time architecture, we can't have these very thick walls, or we can't. So one way to enhance the thermal capacity without the need for thicker walls is to use phase change materials, and we can have, like, in a very thin wall with phase change material, higher thermal capacity, and avoid the fluctuations in ambient temperature. So why the concern in phase change materials? So in the past decade, the energy prices have been increasing, and also another very important reason is the increase in CO2 emissions. So and usually buildings consume around the majority of energy from the total energy consumption. So this is, like, for example, in the undeveloped countries, it reaches like 70%. In Europe, it's about 40%. So, and among these 40% in Europe, there is 45% just for space heating. So it's very important, and it's crucial to find ways to decrease the consumption of energy in buildings, particularly for space heating and cooling. So in summary, the uses of phase change materials are, first, to increase the thermal capacity of buildings, and second, to regulate the thermal temperature to ensure comfort. And sometimes, if used in some latent heat systems, they can store energy during the day or summer to be used in night and in winter. So when designing a phase change material system, it's crucial to identify the thermophysical properties of phase change materials. So first, one of the important things is to identify the thermal conductivity in both solid and liquid phases. The other is to identify the latent heat of fusion, also the thermal capacity in both solid and liquid phases, and the onset of melting and onset of solidification, because it's very important to know when the material will solidify or melt in order to predict the fusion times and to make it coincide with the demand or with the day demand. So, and then the very important thing is the enthalpy temperature relationship, because most of the times we use like a classical traditional piecewise functions for enthalpy temperature relationships, which sometimes have a great impact in predicting the real performance of phase change materials if we don't use the exact or the experimentally obtained enthalpy curve. So since the experiments are costly, so we adopt an experimental and numerical method at the same time to characterize these phase change materials. And we use sometimes, the majority of the times, the inverse method to predict some properties that can't directly be predicted by experimental, and especially like, for example, the degree of supercooling or the enthalpy curve that we've talked about, or even the thermal contact resistance between the enclosure and the material. So they can't be directly inferred from experimental. We need some numerical work. So the problem configuration that we've used is a plexiglass enclosure of about 20 centimeters length and a width of about 1 centimeter. We injected the octadecane inside this plexiglass. Why octadecane? As we said before, octadecane has a temperature melting temperature which lies within the human comfort range, which is about between 26 and 28 degrees Celsius. So it's very adapted for building applications. And also octadecane has transparency properties. Why we need this? Because the ultimate or the application objective when it gets to a mature state would be to use this in glass facades or windows, to inject the octadecane and which can let natural light pass and take advantage of the solar gains. So this is one way to, the most common phase change materials were in concrete or with paraffins in concrete and for concrete walls or gypsum boards, but this is a new idea to implement it in glass facades and windows facades. So the experimental, we'll talk a little bit about the experimental setup that we've been using in the lab in France. So here we have, this is the sample that we've talked about. This is the plexiglass. And this sample is insulated. This is an insulation, and it's put between two exchange plates where we can control the temperature through thermoregulated baths here to control the temperature of the phases. And then this is connected to the data acquisition system where we can extract the heat fluxes and the temperatures of each phase. And from analyzing the data of heat fluxes and the temperature curves, we can determine the thermal conductivities of both solid and liquid phases, and the heat capacities, and also the phase change temperature and the latent heat. So I'm not going into details through this method because it is a direct integration of the curves to obtain these properties. However, these are not the only properties that we need for a phase change material. They are very important, but we have a lot of other complexities. So this is what we obtained from the experimental setup. So we obtained the heat flux. So as we can see here, this is we have a ramp of increasing temperature from 15.8 degrees Celsius till 40 degrees within 4 hours. This is the curve, the heat flux for the melting side, and this is for the solidification side. Phase. So the first thing we see, they are not symmetrical. So the solidification and the melting phenomena are different. They have different kinetics. So this is here the sensible heat, and then we have like a gradual melting. While in the solidification, we can see that it's more an immediate solidification. This gives us an insight about the enthalpy, the shape of the enthalpy curve. Usually, the enthalpy curve is a piecewise function with a symmetrical look. But when we have this fluxes, we can see that it should be dissymmetric, and it should have a melting gradually or a phase of melting gradually and more direct solidification process. Another thing that we can infer here is this discontinuity in the curve, which points out to a supercooling phenomena. What is supercooling? Supercooling is the phenomena where when solidification happens at a temperature lower than its solidification temperature. Why? Due to some kinetics. Because usually solidification happens through a mechanism of we have a small nucleus that has to increase. So there's a certain energy barrier that should be overcome in order for the solidification to occur. and sometimes solidification doesn't occur immediately at the right temperature due to the because the surface energy hasn't exceeded the volumetric energy of this nucleus. So supercooling occurs. So this continuity shows that we have a supercooling phenomena. Supercooling can has side effects because if it is not included in the design, it can shift the fusion times, and it can so we can have some errors in the principle of the design. So if no supercooling occurs, we should have seen the curve a little bit with more smoothness. So we try to change the ramp to 3 hours to see how this affects the supercooling. Usually, we can see here that it affects the supercooling because supercooling is relies on the kinetics. So it's the rate of cooling, or the rate of cooling of the material would affect the degree of supercooling. Here we still have supercooling, but the degree would change. So the main issues here that would in the design of phase change material, which is octadecane, are the presence of supercooling and the presence of like a dissymmetric enthalpy curve. This means that when we have a dissymmetry, this means that we have soluble impurities in the material which come from the manufacturer. So we have to take it into consideration when we design our model. So the other issue that we have risen is the presence of convection. When I first started working on this sample, my professor, Laurent Zalewski, said that we can ignore convection because the material is just 1 centimeter thickness, the sample. So convection won't be important, and there's only pure conduction phenomena. I did some calculations, theoretical and numerical, and I saw that, well, octadecane has a Prandtl number of 50. And the Reinach numbers that are resulting for this sample are very high. So this means that if convection should be effective. So what we did is that, well, I convinced him to try something. So what we did is that we injected glass powder into the liquid octadecane and left them to settle. And then we put it in the machine, and we heat it, and we can see if pure conduction exists. So then we will see no motion of these particles. However, if there is convection, there will be a current, and the particles will go. So this is a small video. So we placed a camera, and using particle image velocimetry, we recorded. So I don't know if you can see it, but I can gradually see it. There's a motion of these particles. So these particles, this is part of the video. These particles are moving upwards and downwards. So the motion here predicts that convection is there, and it can be very effective and can change the design. So we have to include convection in our design. So to calculate the rest of the thermophysical properties of octadecane, we need to use the numerical model, because prediction of convection can be done without the model, and the enthalpy and the intensity curve also, and a degree of supercooling. So we need the numerical modeling part. So for the numerical modeling, we've been using lattice-Boltzmann method. So why lattice-Boltzmann? Because lattice-Boltzmann is a meshless method, and we have envisioned that we will adopt this code afterwards for phase change materials and textiles or fibrous materials. So we need a good method that can easily be extended for porous materials. So lattice-Boltzmann is a fast first-order differential equation. So encoding, maybe the physics behind it is a little bit complicated, but the coding part is very simple. So I will give a brief view on lattice-Boltzmann method. I don't expect that, because it's a relatively new method, and it uses a little bit another way of modeling. Usually what we do, for example, for fluid flows and heat transfer, is to model directly the Navier-Stokes equations and and the energy equations. In lattice-Boltzmann, we don't do this. In lattice-Boltzmann, we follow a Boltzmann equation which statistically describes the motion, and the motion of particles, and we can infer indirectly the properties from the statistical mechanics point of view. So who is Ludwig Boltzmann? For those who don't know, Ludwig Boltzmann is a mathematician and Austrian mathematician and physician who's regarded as the father of second law of thermodynamics and kinetic theory of gases. Actually, Boltzmann, when he proposed his theory of gases, he was rejected by the scientific society, and he got into depression and committed suicide. Decades after his death, his Boltzmann equation was proved, and then it was transferred to a numerical method, and now it's very popular and used in aerodynamics and a lot of other applications. So it happens. Now, what is the Boltzmann equation? it describes the statistical distribution of particles packed in a fluid. Well, Boltzmann gave an example, is that statistically there's this usually tendency for the particles to go to an equilibrium position. So he gave an example about a chamber, and we bring a fluid and put it in this chamber. The most unlikely thing that would happen is that all the fluid particles will go and stick to a certain corner. This is unlikely to happen. The most likely thing to happen is that the particles will be distributed all over the chamber and in a certain statistical way. So, it follows the Maxwell-Boltzmann statistical distribution, which connects the velocity, which is the mean of the statistical distribution, and the variance, which is the temperature. So when we heat, for example, when we heat a fluid, the particles would move faster. They will bombard the chamber, for example, the walls. This will increase pressure. So there's a relation totally with from the movement of the particles to the global or macroscopic properties. So this distribution describes the number of particles or molecules that are at a certain time and having a certain velocity. So this is the famous Boltzmann equation. It's a first-order differential equation that has a time variation and a spatial variation and a relaxation time, which means that we solve it through a collision term, so that the particles propagate and then collide, exchange energy, and relax to their equilibrium position. So I'm sorry. So this is the F can be either, for example, when we're studying the velocity field, it can be the density distribution. It can be a temperature field. So the same equation we can use it for temperature, for recovering the Navier-Stokes equation or the heat equation. So how to solve it? We solve it through two steps: the collision and the streaming. The collision, the particles collide and exchange energy and relax to their equilibrium position. And in the streaming step, the particles, depending on, so in lattice Boltzmann, the particles live on lattices, and these lattices have directions, have vector directions. So when streaming, each vector or each particle, set of particles will go according to its velocity vector or velocity direction. And then they will collide with others, relax, and update their F.
So what is I in this equation?
I is this vector. So we have in each vector, for example, it depends. This is a Q5, so I goes from 0 to 5. If it's D2Q9, I goes from 0 to 9. So it's the vector, the name of each of the factors here is 0, 1, 2, 3, 4, according to each direction. So here, like for example, here instead of I, we're using A. For example, this is another example for D2Q9. So we sum at each lattice, we sum all the density functions to have a certain property, to have density, to have temperature. So we sum all these vectors in order to have the macroscopic properties. So it's not a direct. It's another way of solving fluid mechanics and heat transfer problems. So in our case, we use two lattice Boltzmann, two density functions, one for the velocity field and the other for the energy equation, energy field. How this connects to Navier-Stokes and the energy equations? We choose this relaxation time in a way connected to the viscosity to recover Navier-Stokes equation. So there is a mathematical procedure that we can use in order to prove that from this equation, by choosing this related to the viscosity, this can lead us to the Navier-Stokes equation. And also here in the energy equation, we can relate this diffusivity to recover the energy equation. So we can add also forces. We can add the Wozniak force to account for convection because we need it in our modeling. And we can add, here we add the source term to account for the phase change. So here's the model that we're modeling with this set, mainly this set of equations. But of course, when we're dealing with a phase change, so there's at least three. We have 3 phases. So we have the solid phase, the mushy zone, and the liquid phase. So what is helpful about lattice Boltzmann is that we can use what is called the bounce back rule, and it can this bounce back can block the fluid flow in the solid phase to render the velocities equals to 0. It can partially bounce back them in the mushy zone according to the certain liquid fraction to partially allow the fluid flow, and that's why we treat this mushy zone as a flow in a porous medium a little bit in analogy with Vogt and Voller's work in enthalpy porosity approach, where he treats the mashi zone as a porous material, and the liquid phase, which is the normal Navier-Stokes equation. So to differentiate between these three phases, we use the liquid diffraction. So the liquid diffraction is calculated from the enthalpy, and the enthalpy is related to the temperature through the enthalpy-temperature relationship. But as we said, this is the piecewise function that is usually known and used, which is symmetric and used for the pure material, melting and solidification. However, from our experimental part, we can inversely infer what is the enthalpy, and we can prove that it's related to a certain number of impurities. So this is the enthalpy curve, which shows a progressive melting while a more direct solidification, and this is relevant with the heat fluxes from the experimental part. This part here is for the supercooling. We introduced a nucleation condition that doesn't allow us to go from this one to this part of the curve unless we dip past this enucleation condition. So that this condition is just in the solidification part, and the melting part, the material follows this the gray one, but in the solidification part it follows this one according to a certain degree of supercooling. And this was obtained inversely. We will see how we obtained it inversely. And this is how the enthalpy temperature will look like when we add the impurities or the factor of having soluble impurities, other than this one for the piecewise function. So what are, in summary, the modeling issues that were faced here? The soluble impurities, and we solved it by adapting the real enthalpy temperature relationship. Of course, adapting different thermophysical properties for solids and for liquid phases. So we use the experimentally obtained thermophysical properties in order to better predict the performance of the phase change material. The convection was treated by the lattice-Boltzmann method with a partial bounce-back approach for the mashi zone. The supercooling was treated by adding this enucleation condition that is translated into this curve that we've seen it in the previous model. So we adopted somehow a numerical and experimental way at the same time. And we inversed it. So for example, for the supercooling, we don't know the supercooling degree. So we put a supercooling degree, and then we model, and then we try to fit our model into the experimental results and infer inversely what is the degree of supercooling. So for example, this is a comparison between the numerical and experimental approach. So here's the numerical in red, the experimental in blue. So if the convection is ignored, we won't have this fitting. If it's overestimated, because also we don't know the degree of convection here, it doesn't fit. So we use a little bit some fitting methods. Supercooling, if it's ignored, we can't predict accurately the onset of solidification, and if it's overestimated, we don't predict it accurately. So we use a fitting method and decrease the errors in order to have the experimental curves coincide with the numerical curves. So with the enhanced model, we can see that if we use the soluble impurities, the right enthalpy temperature curve and the convection is then considered, and also supercooling is considered, we can obtain the thermophysical properties. For example, here our degree of supercooling was about 1.2 degrees Celsius. So 1 degree of supercooling was obtained for the 4 hours ramp. So so in summary for this part is that phase change materials used for storage and thermal regulations. However, adequate numerical models should be properly done to predict the solidification phenomena and the melting phenomena, because the convection, if not ignored, it can have an effect on the fusion times and also supercooling. And when we have some lag between our design fusion times and what happens in reality, so our design would have errors, and we can shift from the demand time. So it won't give the desired role. So using Gray or using lattice-Boltzmann model can be very important for treating convection, and also if we intend to extend our method to phase changes in porous or fibrous materials. So this would be a very good model for that. Now, this was my research for the PhD. Now moving on for the for what I'm doing at Harvard. So with Professor James Rice. The first project I'm working on is the formation of channels and deforming tempered ice with Colin Mayer and Professor Rice. So how I ended up on this project, well, ice is a phase change material. So because I know a little bit, or I know a lot about phase change materials, so I was gone through this project about melting of ice sheets and glacier dynamics. So the challenge was that when I first went to Harvard, Professor Rice put me in front of this picture and said, well, this is not a tunnel, like you think when you look at it, it's not a tunnel bored by human machines. Well, it's a naturally created tunnel in glaciers and ice streams. So what we need is that, well, ice, tempered ice is a polycrystalline material. So water lives in a triple junctions of micrometer scale. And the challenge was that he wants me to vision a way to nucleate a channel of meter scale from this tempered ice of water living in microscale. So this was a real challenge, and if you want to know more about what we did here, I have an abstract here about our work that have been finished and submitted. So the idea here for me was a bit a challenge because going from this length scale to that length scale is not very obvious. So thanks for my background in civil engineering, so I proposed something a little bit different than what was already done or what they were thinking of. And I proposed something that is a little bit related to what happens in dams, which is the piping failure that happens in dams through the excess of pore pressure that can open a gap somewhere under the glacier, and then the flow of water and heat dissipation would enhance melting, and would go through from no channel to a channel under these circumstances. And it was a successful, and we're now in the phase of publishing this work. The other project I'm working on with Professor Rice and graduate student Joe Young is the man-induced seismicity. So how to make an earthquake. This is a very interesting topic, especially in the US and in Europe, because of the consequences and the catastrophic consequences induced seismicity have been affecting the lives of people. So this is from Oklahoma. So 3 million Americans are at risk of a human-induced earthquakes this year. And this year also, the magnitude of the earthquake had reached more than 7. So this is a catastrophic earthquake. And the main reason is the presence of oil and gas extraction companies or processes happening near some faults in Oklahoma. So this has been gone for years. And stopping injection won't solve the solution, because we will see afterwards that sometimes stopping injection would have a certain poroelastic response and create bigger or higher magnitude earthquakes. So just one a little bit background on how generally earthquakes occur. So earthquakes occur from a slip on faults. So the main ingredients for this slip either is the increases in the total stresses or the Coulomb stresses beyond the background stresses, or the decrease in the shear strength or the friction on the fault. So these are the main ingredients. So how can we contribute to that as human beings? So how can man induce earthquakes? So either by altering the stress field or by decreasing the strength. And both are from industrial work, from oil and gas extraction, from injection of wastewater, from building dams. So any work that changes the loading and the stresses in the earth near a certain fault can be affecting. So here, the first thing is nucleation can happen due to the decrease in the shear strength. When we inject fluids, the pore pressure increases. The pore pressure is related to the shear strength by the Coulomb law, more Coulomb constitutive law. So this would decrease the increase in pore pressure will decrease the shear strength, and the slip will occur. Another thing is that the increases in the total stresses. For example, when we extract or even when we injecting in reservoirs, for example, may lead to an expansion of these reservoirs. This will induce another stresses and can create slip on existing faults. So the general idea is what we can do about them. So major induced seismicity comes from the oil industry, and we know oil is money, so we can't stop this, especially in wastewater injection. So we can't stop it, but we can analyze and minimize the risks. So we can find some ways to minimize the risk of having large magnitude earthquakes. So for example, one of the biggest threats are the wastewater injection. So water is injected, wastewater from oil and gas extraction is injected in very deep reservoirs. So our tasks here in this project is to study the mechanism, the possible mechanisms of nucleation of these earthquakes first, and second, to propose some strategies. We can't stop them, but we can propose some strategies for the injection to avoid at least high magnitude earthquakes. So one of the things is that either we do some certain injection strategy, or for example, if we start injecting and we have some microseismic events, when we have to stop in order to have that, if we stop at magnitude 2, we may have magnitude of 3. So we can have we should stop when our seismometers, for example, give us a microseismic events of a certain. It depends on the fault and the fault orientation. So there are a lot of propositions and the strategies that we can work on to avoid at least the high risks for that. So and again, the analysis show that stopping injection directly due to the poroelastic response of rocks can have a very high magnitude earthquake. So we proved through some simulations that if we gradually stop this injection, we can at least avoid this near the injection field. Far in the far field, we can't avoid the increase in pressures there. So our purpose is now is to address this question: how to not make an earthquake, how we can propose strategies by understanding the nucleation mechanisms to minimize the risks and not make earthquakes from oil and gas industry. So this is what I'm doing right now at Harvard. Finally, some fast perspectives. I don't know if we're still okay. Fast perspectives about what I think of research in Lebanon. So combining what I think from my background in both geomechanics and thermal performance of buildings, my aim, which is a long-term dream of me, is that to reach somehow in Lebanon a net zero energy building. And this is one of the projects that I've been thinking of. I've been making proposals and I've been working on that. And I think this is one of the projects that can collaborate or that can join different disciplines and different departments, from mechanical, electrical to social departments. And why it's like, I think net zero energy buildings have been adopted or have been applied in Europe and in USA, but the return period was a little bit more than expected because of they have cheap energy. But we in Lebanon, maybe the return periods would be very interesting because we have like the highest, we import most of our energy. We have the most costly energy fees that we pay. We have an electricity crisis. So obtaining or reaching a design concept for a zero energy building is one of the dreams that I have. And I think it's very applicable, and it just needs some collaboration between different disciplines in engineering. For the short term, I think that which would be part of reaching this zero energy concept is working on geothermal piles. Why geothermal piles? Because it combines my background in geomechanics and in thermal and heat transfer. And I've discussed this with Professor Rice, and because Boston is now shifting to more the geothermal energy and has very promising plans for the coming years, so they're very interested in this project, and we can have like certain collaboration with different universities. The other theme, which would be a continuation with the working on induced seismicity, and is very important also for our Lebanese case because of the coming era. And because we are in a very high seismic zone. So in summary, through my experience and that I have acquired from the different work and the research and teaching, I can conduct and propose and implement good quality research and engage in the community service, which is my passion and development of my country. So thank you. Thanks for your attention. Ready for questions.
Thank you.
You're welcome.
Dr. Alissar. I think being at Harvard, where you are in engineering and science, you showed really how these is combined and bridged together. We'd like to have questions from the audience, also from the faculty. We're going to meet with Dr. Alissar at the department, but so this is more open to all now.
Can I ask a question?
Yes, of course.
I got interested in this phase change method. Okay. All the presentation you did, and Majdi was happy. I didn't understand anything. And he reminded me of pussiness. Anyway, what I'm interested in is it practical? Has it been used? And you said injection of the material. How about having an external wall, masonry wall? How do we inject this material? What kind of injection?
Okay.
The practicality of it.
Okay. Actually, the more applicable till now was the concrete mixed with paraffins, with paraffin powders or microencapsulated phase change materials. And this is not an injection thing. The injection I was talking about the plexiglass, which is an enclosure, which we inject with a piston, with a syringe for the material, because it's a plexiglass with a void, and we inject through the void. But what happens in concrete, which is the main application that is used worldwide, and it was used also in I think in Qatar in one of the stadiums. So and it was very applicable, and it's known that it's very applicable in hot climates. In France, we tried, and we have a lot of experiments that they were done. But because of the cold climate of France, the phase change material works more like as an insulator. But as an applicability with concrete, it's used worldwide. Like you mix powder of paraffins, which is a phase change material, with the concrete, or we have there is a micro-encapsulated, which there would be the phase change materials inside this micro-encapsulation, and they are put in the construction materials. But the plexiglass thing is new. It's something that haven't been applied yet. It hasn't reached yet the maturity to be applied within glasses and glass facades. Yes. It's still in the phase of preparation and of study. Yes?
What about the cost of this application in large-scale structure, and what would be the toxicity of used chemicals in demolition waste?
For the phase change material? Actually, the cost depends. Like Octadecane is a cheap product. It's not very costly. And even, for example, if we are considering paraffins in concrete, it's also a cheap product. So the cost is not something that we worry about in comparison with respect to the saving of energy. And Octadecane, if we are considering it in plexiglass, there's no chemical interaction or chemical reactions between it and the plexiglass. But what is known about, for example, salt hydrates, which are some of the phase change materials, that they have to be put in a certain macro encapsulations in order to avoid any chemical reaction with other materials. So in our case, it's not important, but in other phase change materials, it may be something that we have to look at. Yes.
What's Octadecane in its natural state? When I go out and see, what's Octadecane?
Well, it's
Is it a liquid, a gas in its natural state?
It's either a liquid or a solid. It depends on if it's a.
But in its natural state, it has ambient temperature and pressure.
Okay, if we consider it depends. Its melting temperature is about 27, between 26 and 28. So if it's in a temperature, in a room temperature with this and that, it would be a liquid, a solid, and if it's more than that, it would be a liquid.
And I want to quantify the benefits of using this phase change material inside the plexiglass. How much energy would I gain, or how much insulation would I gain as compared to air? If I look at the double glazed window versus with air in between, or with Octadecane.
Well, the latent heat of fusion of Octadecane is 250,000 kilojoules per kilogram. So it's higher. It has a latent heat of fusion very high. Well, air doesn't have, because air is not a phase change material. But what is important about this is that, as I said, because of this melting and solidification, it can absorb the excess of this heat and increases like some thermal capacity of the wall if it's used in wall or of the glaze.
Let me ask a question in a different way. I have an insulated room with a window, and the sun is hitting this window. If this window is double glazed with air, I'm looking at the temperature inside this room versus the Octadecane. How would the temperature change between the two different
This is a very important question, and this is something that should be done because our work was more on the material characterization, but the ultimate or the second one that would have should have completed should adopt this for a building, like even for a small room, and we see what's the difference. But what I expect actually is that the difference is first the thermal fluctuations that we can, if we record the thermal fluctuation in the ambient temperature, it's expected to be less when we use a phase change material because of this solidification and melting phases. So this is one of the things that
numerically you cannot try to predict.
You can, but you have to you have to create a model of, like, we haven't done this because we're more concerned on the characterization of the material itself. But this material, once characterized and once we have all the properties, we can adopt it in a, for example, energy plus model or another software, for example, that takes a building for a total building and tests the phase change material with respect to conventional walls or glaze or windows.
Can I ask one more question?
Go ahead.
We're talking about phase change material, and I know nothing about phase change material. Why did you pick Octadecane? That's something else.
The first because this is the material that hasn't reached maturity. So like there has been a lot of works on concrete with paraffins and a lot of things. First, Octadecane was not done. No transparent material was tried. They have tried to do it for glass or something like that. So this is why the idea came to use Octadecane, because it happens that it has melting temperature within the thermal comfort of human beings, and it happens to be transparent. So it would be applicable for glass and for windows. That's why.
Alissar, actually, I had 3 questions, but I think you answered your answer to all of them. The third one, so I'm trying to think in what weather conditions, how this phase change material would work, and where would it be ideal. Did you comment on whether it works better in colder climates and hotter climates, and climates where you have swing temperatures?
When it was tested, it worked better in hot climates, and unfortunately, in cold climates, as I said before, it acts as more like an insulator than as a material that stores energy and releases energy. So this is from experiences and from materials in concrete, usually in concrete with paraffins, have been suggested this, like they have confirmed this, that the phase change materials in their current situation work better in hot climates. Now what's being done is that they are trying to incorporate phase change materials in latent heat systems, like in a system that you can use different styles, not only like in walls injected or mixed with concrete or injected in windows. Another thing is that what I wanted to say, as I said, it has been tested in the Gulf, and it was successful, especially for paraffins with concrete. So I think the hot climates are more perfect for this material.
Any of our research students?
I have a follow-up question to George, actually. So you're choosing Octadecane because of its properties and whatnot. Is there any sort of reports or work that have been done on this before, and you just taken the model and you studied it numerically?
No.
Where did the idea come from?
Well, the idea came from, there had been work on Octadecane, but not as a phase change material or building applications. Octadecane has been used traditionally and from previous years as a benchmarking problem for convection. So like all the benchmark problems that you see in literature from the years of Brent and Vaughan Voller, they all used octadecane as a very highly convective material and tested it like just for like developing models, finite volume models, finite element models, through a large benchmark problem, where there were like many or a lot of number of scientists that have participated through this workshop. It was on octadecane, but no one has thought before about this because it wasn't like something that that these people particularly were thinking of. So from there came the idea of using phase change octa.
There's like, let's say like a natural disaster or a fire or something, how playable is this material and how dangerous would it be, or how would it make the situation?
Actually, I don't have like exactly what is known about it. It's not like there's no risk on that, but I think when it comes to the mature state, these things should be tested in all cases. So so currently, this is what I have.
Does the melting and solidification of the octadecane inside the isolation cause any internal stresses?
We thought about this, but no, because the expansion, the thermal expansion of the material isn't like it has a low thermal expansion. So if not, it would have like cracked the plexiglass that we've put in.
Okay, I guess we have no more questions. I'd like to thank you, Alissar, for putting this presentation. I know you were asked to do so many in 1 hour, and I think you organized yourself very well.
Thank you.
This was enlightening. And again, thank you for the students who were requested to attend. And the next time I will say required so that, no, you know the trick.
Okay,
so,
thanks for your attention. Thank you.
Okay, so I guess faculty members are invited now to the meeting. Anyone who would like to have an abstract about the work we're doing at Harvard, there's... Okay, so we're going to room 435, okay? Not 537, please. 435.